Hey, Mr. Sams, what are you drinking?
My solution.
Your solution.
Yeah.
Yeah, I can tell that. I need coffee.
No, I teach, therefore
I need
I
coffee.
need coffee.
But you know, I teach too.
Yeah.
But
Get your own little fix
I
there.
got my solution here. It's called Focus Kiwi Strawberry Vitamin Water.
Uh-huh. You have your solution, I'll have mine.
There we go.
Mhm.
So we're talking about solutions today, guys.
Mm.
Solutions like solutes and solvents, and of course, my solution is a solution with it's an aqueous solution with water.
Yeah.
And if I kind of look carefully, I could probably even figure out what is water is the what?
That's our solvent.
Solvent.
Mine also has a water solvent.
Yes, because yours is that coffee.
Yep.
But mine has what's dissolved in it would be like the solute. I have cane sugar. I got citric acid.
There are over 250 compounds in a coffee bean that contribute to the flavor of coffee. Did you know that?
250.
Yeah, so mine is
One including caffeine.
One is caffeine, and that's the key one. Without that,
I don't think there's any caffeine in this.
no.
You probably need caffeine. It is early in the morning.
It is, yeah.
You see, Mr. Sam's is not a morning person, and it is 7:45 in the a.m.
And
I've been up for 2.5 hours.
I might note that we did just have the time change this weekend, so it actually feels like 6:45.
There you go. Well, see, I've been good. I got up, exercised, worked
Yeah.
out on the bike. Yeah. So today, let's dive in and start talking about solution. Yeah. All right, 3 main topics today: solution composition, the energies of solution formations, and the factors that affect a solution formation.
All right.
All right. So we've already kind of alluded to this, but let's just get some meat on those bones.
Yep.
What is a solute?
Solute's the stuff that you put into the solvent.
The stuff dissolved.
The stuff that gets dissolved, yep.
You can say gets dissolved. I like that. And then a solvent.
Is the stuff the solute gets dissolved in.
Dissolve.
Dissolver.
Medium is how I...
Yeah. So if,
Or the dissolver, I like that.
yeah. Just, if you have salt water, salt's the solute, water's the solvent.
Yeah, and together they make
solution.
a solution. All right, it's a mixture, basically, folks. It's a mixture, and then one thing is sort of the thing that you have most of is considered the solvent,
Yep.
and the less is that. Well, a solution, yeah.
And
That's,
specifically, it's a homogeneous mixture.
yes, so let's actually write that down here. It's the homogeneous mixture.
Homogeneous mixture.
And then solubility is a little bit different, isn't it? It's a
Yeah,
it's a
how
mathematical
right,
term,
that's
isn't
how we
it?
measure the extent to which something dissolves.
So it's a number. So how do we do that? So that's basically the amount, actually the maximum amount, right?
Yep.
The maximum amount, A-M-O-U-N-T, amount of solute in a given amount of solvent. Typically, it's given in grams of solute per 100 grams of solvent. All right, so that's the maximum amount, okay? So here's some examples of some different types of solutions.
Oh, yeah.
So most of the time, the solutions that we alluded to at the beginning of the podcast, of course, were aqueous solutions, where water was the solvent.
Yeah.
But actually, there are lots of different varieties of solutions you
There
probably are
are.
not familiar with. The one we just talked about was this one right here. We had the liquid was the state. The state of the solution was is this right?
I think that's a typo. Let's fix that.
Yeah, this would be wrong. This is the state of the solution would be a liquid, and the state of the solute would be a solid. There we go. That's what it'd be. That would be like salt water right there, or seawater, so salt water. Okay, it's a little typo there. Air, natural gas, is actually a solution. So what you're breathing right now is a solution where the gas and the solute are the same, gas. So you've got oxygen and nitrogen. They're dissolved in each other, really.
Yep.
Or vodka and water, okay, or antifreeze, liquid and liquids, two liquids dissolved in each other. We'll actually show that in a little bit. Solid would be like brass. Two solids dissolved in each other. It's kind of an alloy. Carbonated water, you have a gas. These are backwards, aren't they?
Yes, they are.
So this would be a liquid, and this would be a gas. So this is a carbonated beverage. I don't have a carbonated beverage with me today, but the gas is dissolved in the liquid.
Yeah.
And then hydrogen and platinum, I think I still got them backwards, don't I?
Yes, you do.
I think what I probably did is I messed
Probably
it up
just
here.
yeah, I messed up your. Kind of messed it up.
Solid, and this is gas. Okay. Oh well.
No worries.
Yeah. All right. So you get the idea. There's different kinds. So you can have a solution that can be a solid, a liquid, or a gas. And what's dissolved can also be a solid, a liquid, or a gas. So, kind of cool. Now notice there's no solids, though, dissolved. Never mind. They throw it. All right. Now, we can measure solutions.
Yep.
We can measure their concentration.
Concentrations.
Now, solubility is a measure of the maximum amount, but if you have some that's less than the maximum,
Yep. Then we can measure how much of it is dissolved in there specifically. Now, we've talked about molarity before, and that's the moles of solute per liter of solution. Now, it's very important that you keep track of the terms here, because in molarity, it's moles per liter of solution.
Solution.
Now, a new term we're going to introduce today is called molality, and molality. I hate that word. It just sounds weird. All nasal.
I like it.
Molality. Anyhow, it's moles of solute per kilogram of solvent, not total solution per kilogram of solvent. That's a very important distinction.
You get all messed up if you try and think of it per solution.
Yes.
All right. And then there's mass percent, mass solute per mass of solution.
Times 100, more specifically.
Actually, yeah, we should say times 100 there, yeah. And then the mole fraction. Now, this is something that's new in the mole fraction.
Right.
It is just the percentage of moles, really,
Yes.
as a decimal, not as a percentage.
Right.
So you take the moles of whatever chemical it is, A or whatever, over the total number of moles. And we'll do some examples so this is clear for you. In fact, speaking of an example, let's do one. Now, this one has quite a few questions on it.
Yep.
Okay. All right, so in this example, we have isopropyl alcohol, and we know its density. And we've got grams and we got grams. What is the molarity, the molality, the mole fraction, and the percent mass? All right, so to do this, we need to kind of just think it through. I like to kind of convert things to moles first.
Yep.
Moles seems to be the best work. We've got this isopropyl alcohol, which probably we should know its molar mass. So if I've got 20 grams of isopropyl alcohol, I'll call it IP. I'm going to convert that to moles. Now, isopropyl alcohol is... The formula is C3H7OH. So, Mr. Sams, what is the molar mass of C3H7OH?
I suppose I should be calculating that, shouldn't I?
Be 20, 36, 39,
60.
40, 60, yeah. So 60 grams in 1 mole. So Mr. Sams is going to determine how many moles of isopropyl alcohol we are. So 20 over, 2/3.
Yep, 0.333.
0.33 moles. I'll just use IP for isopropyl alcohol. And then we've got 40 grams of water. To convert that to moles, of course, there are 18 grams in 1 mole.
2.22.
2.22 moles. Now that we have the moles, we can do quite a number of things. Okay, so I have 0.33 moles. So let's do the mole fraction first, something that's sort of a new thing for you guys.
Right.
So I'm going to take the mole fraction. The mole fraction is the moles of the isopropyl alcohol, which is 0.33, and I'm going to divide by the total number of moles, which was
2.22 plus 0.33.
2.22 plus 0.33. So this would be a pretty high percentage. I'm going to say 9.9 something. Am I right? No, low number.
Low percentage. Yeah, it's 0.13.
I was going the other way. 0.13, and there are no units
No.
in mole fraction.
No units.
So that is the answer. That is the mole fraction of this. Let's next do the molality.
Should we talk about mole fraction of water? Because we can do
Did it ask for? Did it ask? Yeah.
I don't remember if it did.
Well, let's go for it.
Yeah, they're
the
always
mole
going to
fraction
add up
of
to
water of 1. Yeah, they'll add up to 1, and that'll just be 2.22 over 2.22 plus 0.33. Or actually, you could subtract from 1, get the same answer. It'd be 0.87, right?
Yep, 0.87.
Now, I knew that, of course, because 0.13 and 0.87, they add up to, they add up to 1.
Yeah.
So that's not terribly difficult. Let's do the molality next.
All right.
Now, something on molality, folks, is the symbol for molality is a small cursive M, not a capital M for molarity. Now, molality is moles of solute per kilogram of solvent. Now, the moles of the solute is 0.33 moles of the isopropyl alcohol, right? Divided by the kilograms of the solvent. The solvent in this case is water. Now, if you recall, they gave us that there were 40 grams of water. Now, that would be 0.04. I'm doing this in my head. Hopefully you can do that. Follow along. 0.04 kilograms. Of course, to get from grams to kilograms, you divide by 1,000. That's it. You take 0.33 divided by 0.04, and you get an 8.25 molal solution. That's good. And you say molal.
Molal.
Molal? It is the molal solution.
Molal.
Yeah. So now, what else do we need to do?
Molarity.
Actually, I think we can do the percent. Let's do that because that's easy.
Oh, yeah.
It says, what's the percentage, right? Does it want it the percent?
It does.
The percent mass. That is super easy. It's just the percentage. I can do this in my head. You see there are 20 grams of isopropyl alcohol in 60 grams of solution. Now, where did I get the 60?
It was 20 grams of isopropyl alcohol plus the 40 grams of water.
Right, there were 20 here and 40, so the total is 60. So that's a 0.33, isn't it?
It is.
0.33, and that would be times 100, actually. So,
oh, you're right. 33%.
So that would be 33%. All right, lastly, the molarity. The molarity is actually the hardest one.
It is hard on this one.
So the molarity, if you recall, is moles of solute per liter of solution. All right, now we have another number that's very important. So let's start with our moles solute. We know we had, wasn't it 0.33? So we have 0.33 moles of solute, and it is in 60 grams of solution. We just kind of did that in that last one, right?
Yep.
Now I need to get this number here to liters.
Yep.
All right, so we know the grams. So now, but the cool, let's go back to the data or the question itself. This is very important, this number, 0.785 grams per milliliter. And actually, this is a bit of a typo. This is the density of isopropyl alcohol. It should be of the total solution when we're done. So we need to know the density. So it's 0.785. And watch how I do this. I can say 0.785 grams of solution per 1 milliliter of solution. That's the density, grams per milliliter. Now my grams of solution cancel, and I want it in moles per liter, but guess what? I've got mLs down here, so I can say there's 1,000 mLs in 1L. And my milliliters cancel, and I now have moles per liter. So you take 0.33 divided by 60 times 0.785 times 1,000, you get a
4.32.
4.32 molar solution.
4.3, I guess, sig figs.
4.33?
No, 4.3.
Just 4.3 sig fig. Okay, so 4.3 molar solution. So you can convert from one to the next. And why do we have different units of concentration? Why don't we just stick to molarity? That'd be nicer, wouldn't it?
Yeah, well, some things, when we get to the end of this chapter, you'll find that in order to do the calculations, you actually have to use molality.
So there's different purposes for different measures of concentration. These all are saying the same thing. A 4.3 molar solution is the same thing as a 33% solution in this particular example, and an 8.25 molal solution, or a mole fraction of actually 0.13. They're all the same measurement of the same thing, but just in different units.
Yep.
It's like saying you're going 55 miles an hour, or you're going, I don't know what it would be.
The equivalent kilometers per second or whatever.
Yeah. Okay. Let's do another one because these can get kind of confusing. The molarity of concentrated ammonia is 14.8 molar. As a density, okay, what is the molality, the mole fraction, and the percent by mass? So it's a similar one, but when they start at molarity, it gets kind of tricky. And so when we do molarity, that means it's ammonia. Now, what is ammonia? That's NH3. Remember that, guys. So 14.8. 14.8. Now, watch what I say. I'll say moles of NH3. And I'm going to assume that I have 1 liter of solution, right? That's per liter. So it's 1 liter of solution.
Right. Because molarity is moles per liter.
Technically, I could write this, but these are actually like data points. We're going to start with this and this sort of separately.
Yes.
All right. So if I want to do moles per, I need to figure out the number of grams of water, don't I? Essentially, don't I? Or mole, because it's in water. So I'm going to take my 1 liter of solution. That's where I'm going to start. And I'm going to say 1 liter is 1,000 milliliters. So I'm going to use my density first. And then I'm going to say that 1 milliliter is equal to 0.880 grams. This will give me the grams of solution, which is going to be
880 grams.
880 grams. Now this is solution.
Right.
That's combination of ammonia and water.
So let's take those moles of ammonia and convert that into grams.
That's what I was just thinking. So we can say 1 mole is 17 grams. So how many grams of ammonia do you have?
251.6.
251.6 grams of ammonia. Now, that remainder, of course, or the difference, so if I take 880 minus 252 sig figs.
Okay.
I'm going to get
628.
628 grams of water. Now that's important. Now that I have this grams of water and the grams of ammonia, I can now do some problems. Now the other thing that's going to be helpful in solving this is it's nice to have the moles of the water. So if I have 628 grams of water and I want to convert to moles, there's 18 grams in 1 mole. And of course Mr. Sams has
34.9.
already gotten that moles. Okay, so let's do the I don't know, percents, because in the percents it's the amount over the total. So the percent will be 251?
252.
252 grams of the ammonia divided by the total, which was it, 880? 880 grams of solution times 100 gives me
28.6.
28.6%.
Percent ammonia.
Percent ammonia. For the percentage, the other one, it would be 100 minus that. To do the mole fraction of the ammonia, that will be the moles over the total moles. Now, we had the moles calculated. Actually, it was just given 14.8. So that'll be 14.8 moles over the total moles, which will be, what was the number, 34.9? So that'll be 34.9 plus 14.8. Put that in parentheses. There are no units on that, and when you get that, you get a 0.30. So we've done 2 out of the 3.
Yep, that's the mole fraction of the ammonia, then 1 minus that would be
and by the way, the way we
fraction of
write this,
water.
it's a funny X. There's a symbol for mole fraction.
Chi.
Chi, actually, yeah. And sub, and then you write the chemical, ammonia. Now, we still need to do the molality, right?
Molality.
The molality is pretty easy, actually. It'll just be the moles, which was 14.8 moles of the ammonia, divided by the kilograms of the solvent. Now, we had 600 and something, right? 628 grams of water, so that's really easy. That's 0.628 kilograms of water, and that's it.
Yeah, 23.6.
Wow. That's a very well, it's concentrated ammonia.
It is.
This is dangerous
That's
chemicals,
nasty,
actually.
nasty stuff.
Is that all we need to answer? I think.
Molarity. No molarity was given. Molality, mole fraction, percent.
I think we've got them all.
Wow.
How good are we?
So again, guys, just to summarize, when you're doing those, get grams and moles for the solute and the solvent first before you do anything.
Let me write that down.
And then you go in and do the rest of the math. It's real easy after that. Grams and moles of both solute and solvent. And then do the math. And you guys are good at math.
You rock at the math. All right. All right, now we're going to move on to a new topic. I'm choking up a little. It's so good.
Perhaps you should drink some of your solution.
I should drink some of my solution. All right, today, love that vitamin water.
I'm pretty sure that color doesn't occur in nature, though.
This is true. Okay. Why do things dissolve?
Because they get attracted to other particles other than themselves.
There's actually sort of 3 things that happen when you have something dissolve in something. All right? Well, the answer is there actually is some attractive forces. So it's related to, say, Chapter 8, or if you've been watching the podcast, Chapter 8 podcast, where we learned about how things work in terms of bond energies and stuff like that. And you notice you see some delta H's here. We've got an H1, an H2, and an H3. Essentially, in step 1, or delta H1, you must have the solute expand or separate. And that requires energy. That amount of energy we're going to call delta H1. You also need the solvent to kind of spread out so it can make room for the solute. So it also needs to expand, and that is what we're going to call delta H2. Now, both of these will always be endothermic, meaning it requires energy to expand the solute, essentially to break the bonds of the solute to itself, and the same for delta H2, so it will always be exothermic. Endothermic. I said exo. I meant endo, and I wrote positive. It's endothermic. Endo. Okay. However, then there is a third step. Is you see the solute, which is blue in our picture, and the solvent have to be attracted to each other.
Yeah.
And if they are attracted to each other, they like each other, then you will have a third delta H, and that's delta H3, and it will if it's attracted, it will be negative. If it's not attracted, it will be positive, and then actually it will not dissolve. Because for this to actually work, you need to have the net effect as you must have a exothermic reaction or it will not dissolve. Okay? So here's actually, well, same picture with expansion. Here's actually the picture I was looking for. So if you do delta H1 and delta H2, which is always endothermic, hence the arrow going up, the orange arrow, and delta H3 being negative, highly negative, what's going to happen is the delta H of the solution will be negative, and the reaction, or the substance, will dissolve. Now, if we look at the second one, case over here, delta H1 and 2 are both positive. Delta H3 is negative, but not very negative. The delta H of solution will be positive. And actually, this will still work.
Yeah, it'll still dissolve.
But if you get too much, if this number's too big, then it will not dissolve. Actually, if this is still negative, it's still negative, yeah, so it'll work. But there are instances, and we'll show you an example of that in a couple of minutes, where they don't dissolve. Okay? So let's illustrate this with a little demonstration. So here I am with some calcium chloride. And in the beaker, I have some water, and you can see I have a temperature probe, and so you're seeing the temperature. What's the temperature, Mr. Sams?
18.7.
So 18.7. And so I'm going to put some calcium chloride into the water so it will dissolve. All right? So as I pour some calcium chloride dissolve, it is now dissolving. All right? Let me now stir this up here. And you should see
19,
the
20.
temperature rising. What's happening is that delta H3 that we talked about is very, very high.
21.
So this is a very exothermic heat of solution. So as it dissolves, and you can see little pellets are dissolving, the calcium chloride is expanding. The water is expanding to accommodate it, and the delta H3, the attraction between the calciums in the water and the chlorides in the water, is quite exothermic, and so this reaction, the temperature, should be significantly higher than it was before,
Yep.
as you can see. So just we're watching something dissolve, but we're also seeing the temperature change, and we can actually calculate the heat of solution. We did this lab actually in our classes, and so this is just this is why this dissolves, because that high value of delta H3. All right, so now we're back to the screen, and we can see how that all works. And so in terms of energy, if the delta H1 is large, this is a polar solvent and a polar solute, and delta H2 is large, delta H3 is a very large negative, and the heat of solution is small, and the solution will form. Now, if you have a polar solvent and a non-polar solute, we haven't really talked about this, but we're just about to. You have a small delta H1, a large delta H2, this small, and actually no solution will form in this case. That's when you take polar with a non-polar. You might remember the like dissolves like, which we're going to talk about in a minute, and I'll show you too. It's very good. And non-polar with non-polar, it's small, 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 and actually you'll make a solution. And if you have a non-polar and polar, delta H1 is large, small, small, no solution. So basically most of them get, here's a solution. About half of them make solutions and half of them don't. But the reason has to do with this delta H1, delta H2, and delta H3. That make sense? So we've already kind of said this, but like dissolves. Like. I like you. All right. So that means, but it's not that the red dissolves red.
No,
right?
the like polarity is like.
Like in terms of
Right.
polar. So polar dissolves polar. Non-polar dissolves non-polar, but polar does not dissolve non-polar.
Sort of.
What? What do you mean by
Given enough time, everything will dissolve in water.
True.
With very small amounts.
All right, so let's illustrate that with a demo. Okay, well I've got some water, and to the water I'm going to add some Karo syrup. All right.
Syrup.
Syrup. So if I add the syrup, and if you look carefully, zoom in on that, Mr. Sands, you can kind of see the syrup down there at the bottom right there. But if I stir it, what's happening is the Karo syrup is a very tasty thing, but you can see there's still some strands, but it's dissolving in there because the Karo syrup is polar and the water is polar. Polar dissolves polar. Like dissolves like. Got it? Okay. All right. Now let's start talking about a next one. So now we're back, and I've got some more water. But instead of having K-rose syrup, I've got vegetable oil. All right? So I'm going to pour the vegetable oil into the water. Now, it looks like it's mixing, but if you look carefully, you'll notice that we have a layer of the vegetable oil where the stirring rod is, and below that, a layer of water. Now, I can mix it up like I did the K-rose syrup in the water, and we can allow it to settle. But notice what did not happen. It did not, and it will not dissolve. So it does not dissolve because you have a layer here of the, right here, of the vegetable oil. There's little bubbles and such. That'll eventually disappear. And then there's water. And so, because the water, of course, is polar, based on its Lewis dot structure and all that stuff, vegetable oil is not polar. Therefore, polar does not dissolve into nonpolar. All right, so yeah, you've seen the cool examples of that. But why is that? Why do polar dissolve polar and nonpolar dissolve nonpolar? Well, it has to do with that delta H1, 2, and 3. I think one thing that a good way to illustrate at least the polar, if I take the water, draw some little Mickey Mouse heads, right? That's the water molecule. And if I were to drop some, we used another polar substance. And remember, what does polar mean? Is that this has a slightly positive charge here and a slightly negative charge here. Or the way we could illustrate that oftentimes is we'll draw an arrow to the negative side, and this is the positive side. If I then put something that has a negative charge in here, or let's take a polar molecule that has a negative end and a positive end, you see there's like a dashed line between here and here. That is an attractive force. This is this delta H sub 3, and then this positive right here is attracted to this negative, and so this polar molecule, which is kind of a oval I've drawn it as, is why it dissolves. Okay, and why do polar not mix with nonpolar? Well, it all goes back to that delta H1, 2, and 3 business. But I think a key thing to understand there is that if you've got something that's polar, it's got a positive end and a negative end, and then you put something in there that has no positive or negative end, there is no attraction here. So they don't dissolve in each other. That was the oil and the vinegar. In nonpolar and nonpolar, you got two substances, and they don't have polarity, so they easily can move. That's an arrow moving it. And this one can slide past each other. Okay? Questions? All right. One more thing I think we're going to talk about. What are the pressure effects of concentration or of solubility? So the higher the pressure, the what?
The more gas that can dissolve in water.
Yeah. Now, you understand this. If you have a can of soda, all right? If you have a can of soda, it has got, of course, carbon dioxide dissolved in water. It's carbonated, right? And so, actually, when they make the can of soda, they actually make it under a pressure of about 4 atmospheres. Mm-hmm. And so what actually happens is we make what we call a supersaturated solution of carbon dioxide in water. All right, and this follows what's called Henry's law, that the pressure is equal to some constant times the concentration.
All right.
All right. Now, we don't need to spend too much time on this mathematically. I just understand that the higher the pressure, I think you understand it more conceptually. I've never seen, for example, in the AP test, a question that involves Henry's law
I think
mathematically.
One in your homework.
But if you do,
plug and chug.
it's just plug it into and they would give you the equation and you would use it. So, and the constant, it's very simple. All right. So here's a way to illustrate it. You have a pressure 1 and a pressure 2. The gases, these are gas molecules. More of them can dissolve when you have a higher air pressure over the top.
All right.
All right. Now, temperature effects. Now, in temperature effects, we have sort of two cases. A solid can be dissolved in a liquid. Mm-hmm. So generally, the higher the temperature, the
greater the solubility.
Greater the solubility. This is for a solid dissolved in a liquid. So this is like salt water. So if I have salt water, basically hot salt water will dissolve
more salt
than cold salt water.
Yeah.
Now, actually, with a gas and a liquid, it's the reverse, isn't it?
Yeah.
The higher the temperature, the
lower the solubility.
Now,
this is applications if you like to fish. Anybody who likes to fish knows that the best trout come from nice icy cold water. Because in icy cold water, there's lots and lots of oxygen. Because the water is pouring over the rocks and it's nice and cold, and as it falls over the rocks, it picks up oxygen from the air, more of it dissolves. So the fish have lots of oxygen. They're real vigorous, and so they have nice strong, tight muscles when they taste really yummy when you eat them. The problem is if you pull a fish out of a kind of a warmish lake, they're always kind of mushy and blah, because you got a lethargic fish because it doesn't have as much oxygen. Yummy. Sad fish.
All right. Important to understand this is a lot of people don't understand this. What does a fish actually breathe?
Oxygen.
Yeah, but a lot of people think that they're actually breathing water.
It's the oxygen dissolved in the water.
Yeah, you see,
Their gills get the oxygen out of the water. Our lungs
there's
get
water,
the oxygen out of the air.
but dissolved in there, in between the water molecules, are little O2 molecules. They breathe oxygen just like humans do, in terms of they need the same chemical. They extract it in a different way out of the solution, where we breathe it directly out of the air. But they need the oxygen. Now, this graph, we should make a note here. This graph illustrates that the higher the temperature, the lower the concentration. Here's oxygen right here. I think it's the blue line there. And so the lower the solubility, so you have a lot more. Now we should go back to this graph. This is a solid, S-O-L-I-D, solid in water. And so you can see generally, now I said this on the text, that generally speaking, the higher the temperature, this is temperature down here, of course, the higher the solubility. So if you look at sodium nitrate here, it gets higher and higher the higher the temperature. There are some exceptions.
Yeah, they tend to be sulfates.
Sulfates, like the cesium, or cerium, I think. Whatever, this sulfate goes down, but generally speaking, the ones
sodium sulfate actually goes down too.
Yes, sodium sulfate does. Ammonia does too. So there's some exceptions. That's actually more of a gas.
Ammonia is a gas.
That's why, so it doesn't apply. So you can see they generally get higher. And so what we said, so this is generally true for solids, but it is always true for gases, this decreasing thing that we see right here.
Yep.
All right. So that concludes today's podcast. We'll see you back.
I'm going to finish drinking my solution.
Oh, yeah. Well, I should probably drink mine too. All right.